Welcome back to this next video in which we are discussing splitting fields. Okay, so we're currently in the process of proving this theorem that will allow us to conclude that splitting fields are unique up to isomorphism. Okay, right, so we are doing this by a proof by induction where we're inducting on the degree of the polynomial, and we've now said that we will assume that the theorem is true for any polynomial which has degree less than n. And now what we want to show is that if that's true, that it's going to be true for a polynomial of degree n. Okay, now this is going to follow a very similar protocol to what we did to prove that the splitting field existed. Okay, right, so what we're going to do now is we're going to split it up into two cases just as we did there. So case 1 is that your polynomial p of x, that all of the irreducible factors of that in the ring of polynomials over the field capital F are of degree 1. Okay, so case 1, irreducible factors are all degree 1. So irreducible factors, degree 1, and I'll just put R degree 1. Okay, now what does that mean? Well, if the irreducible factors of p of x in the ring of polynomials over the field capital F are all of degree 1, then that also implies that the irreducible factors of p prime of x in the ring of polynomials over the field F prime are all going to be of degree 1. So let me just write this down. So remember, p of x is our element of the ring of polynomials over the field capital F, and we've got the corresponding polynomial p prime of x in the ring of polynomials over the field F prime. Okay, now if this one has all of its irreducible factors in the ring of polynomials over the field F being degree 1, then I claim that this one will also have all of its factors being degree 1 in the ring of polynomials over F prime. And the reason is that we know that this ring and this ring are truly isomorphic to one another. There exists that very natural isomorphism between the two. Okay, you're just using different symbols for the coefficients. Okay, so we know that p of x and p prime of x are equivalent in this sense, i.e. if we act the isomorphism pi on p of x, we get p prime of x, and the theory of factorizing any polynomial in here into its irreducibles is going to be identical to the theory over here. Okay, so because these are truly isomorphic, then this algebraic notion of factorizing a polynomial into its irreducible factors is going to carry over between them. So if this one factors into all degree 1 factors, i.e. its irreducible factors are all degree 1, then the same thing will be true for this. So factorizations into irreducibles carry over basically because of how isomorphic these two are. Okay, right, so therefore I can conclude, so because this one it factors into degree 1 factors in the ring of polynomials over the field capital F, then I can conclude that the splitting field for p of x over f is just going to be equal to f, and similarly over here, because this one factors into degree 1 irreducible factors in the ring of polynomials over f prime, I can conclude that the splitting field for p prime over f prime, k prime here, is just going to equal f prime. Okay, and then the theorem is clearly true because we need to show that k and k prime are isomorphic to one another. Well, we started off by saying that f and f prime were going to be isomorphic to one another. So if case 1 is true, then truly the two splitting fields are going to be isomorphic to one another. So again, case 1 is the easy case, and now we're going to go on to case 2, which will require a bit more work. Okay, so we don't need to worry about case 1 anymore. We've done case 1. Now let's do it for case 2. Okay, so case 2 is the case where you have at least one irreducible factor of p of x that has degree greater than or equal to 2. And to stick with the same notation as we used last time, let's say that this factor of p of x, this irreducible factor of p of x that has degree greater than or equal to 2, we're going to once again denote it f1 of x. Okay, that's exactly the notation we used last time. So for p of x, it's going to have this factor, this irreducible factor that must have degree greater than or equal to 2. Okay, if there wasn't such a irreducible factor of p of x in the ring of polynomials over the field capital F, and I think I'll just add that in here. Okay, then of course we'd be talking about case 1. So case 2 is that it doesn't factorize down into all degree 1 irreducible factors, so there must be at least one irreducible factor that has degree greater than or equal to 2, and we're calling that f1 of x. Now I've just argued for the fact that the factorization into irreducibles process is, equivalent to in the ring of polynomials over the field f prime now. Okay, so if we're now talking about the polynomial p prime of x, which is in the ring of polynomials over f prime, then because the factorization process is truly equivalent between the two, then again, if this one has a irreducible factor of degree greater than or equal to 2, which we're calling f1 of x, then there will be an equivalent one in the ring of polynomials over the field f prime, okay, which we'll call f1 prime of x. Okay, and if I take pi of f1 of x, I'll get f1 prime of x. So this is its equivalent irreducible factor in the ring of polynomials over f prime of x, or rather just f prime. Okay, right, so I can find these two irreducible factors, one for p of x and then the corresponding one for p prime of x, and I'll remind you again that if I take the mapping pi and act it on f1 of x here, I will get f1 prime of x here. Okay, right, so what am I going to do next then? Well, what I'm going to do is exactly the same as I did before. So I've now got an irreducible polynomial of degree greater than or equal to 2. What did we do in the proof of existence at this point? We generated a field extension of f using this. Okay, and that's exactly what we're going to do here. So now what we're going to do is we're going to generate the field extension of f, which we'll call E1, and the way we're going to generate this is we're going to take the ring of polynomials over the field capital F, and we're going to quotient it out by the principal ideal generated by this irreducible polynomial of degree greater than or equal to 2, which is f1 of x here. Okay, so remember, this is a field extension of f, so let me just write that down somewhere. So I'll put this here, E1 is a field extension of f. Okay, so we do this, that's perfectly valid to do it, and of course now we're going to do the equivalent process over here. So what should I call the equivalent thing? Of course I'll call it E1 prime. Okay, so E1 prime, I'm going to take the ring of polynomials over the field f prime, and I'm going to quotient it out by the principal ideal generated this time by the equivalent polynomial f1 prime of x here. Okay, and I'll colour that all in orange, and clearly E1 prime here is going to be a field extension of f prime. So E1 prime, is a field extension of f prime. I was about to write is equal to f prime, is a field extension of f prime. Okay, so that's perfectly valid. We can build these field extensions of f and f prime. Now, what do you think is going to be my next line? Well, my next line is, of course, that E1 is isomorphic to E1 prime. Okay, now let me give you an informal argument as to why that is true. We know that the ring of polynomials over the field f and the ring of polynomials over the field f prime are isomorphic to one another. They're equivalent up to the fact that you have different symbols for the coefficients. Okay, utterly equivalent algebraically. We know that these two polynomials, f1 of x and f1 prime of x, are equivalent under this isomorphism. So these principal ideals generated by them are equivalent. So we're quotienting out equivalent algebraic structures by equivalent principal ideals in them, so we're going to get equivalent algebraic structures here. So truly, E1 and E1 prime are going to be isomorphic to one another. Excellent, right. So now, what can I say is going to be true in the ring of polynomials over E1 and E1 prime? So now what we're going to do is we're going to work with the ring of polynomials over the field E1, and we're going to work with the ring of polynomials over the field E1 prime of x. Okay, sorry, I keep saying of x. The ring of polynomials over E1 prime, it shouldn't be of x. Okay, I apologise for continuously adding in that of x. Okay, right, so now what can we say in here? Well, of course, in these extension fields of f and f prime respectively, we are now suddenly going to have a root to the polynomial p of x, okay, because we're going to have a root to f1 of x and f1 prime of x, and of course if you've got a root to these factors of p of x and p prime of x respectively, you're going to have a root to p of x, okay. So suddenly, in the case of the polynomial the ring of polynomials over E1, we're going to be able to write p of x as x minus alpha 1, so I'll call the root to the polynomial f1 of x that is added into this field extension of f here, E1, we'll call that alpha 1, okay, sticking with the 1 notation here. And now, of course, what that allows us to do is in the ring of polynomials over this field E1, I can factorize p of x, which is obviously still an element in there because E1 is a field extension of f, into x minus this root, alpha 1, times what's left over. And again, sticking with the notation from the previous proof, I'll call this p1 of x there. Okay, and note that p1 of x will be some polynomial in the ring of polynomials over the field E1 here. Okay, right, so that's what I can say for that one, and I'll underline all of that in yellow here, sticking with that. Okay, and then we can do the equivalent thing over here now. So I can take p prime of x, and now there'll be a root to that in the extension field E1 prime here. We'll call that alpha 1 prime, and of course if we take the image of alpha 1 under this isomorphism here, and I know I haven't given the isomorphism a name, but if there will be an isomorphism between these, a very natural isomorphism, then alpha 1 would go onto the equivalent root over here, which we'll call alpha 1 prime, and then it'll be times some polynomial which we'll call p1 prime of x. Okay, and I'll colour all of that in orange. And of course, p1 prime of x will be an element of the ring of polynomials over the field E1 prime, and this polynomial and this polynomial will be isomorphic to one another in the isomorphism that there will also be between the ring of polynomials over the field E1 and the ring of polynomials over the field E1 prime. Okay, so we've already have seen this. If we've got two fields that are isomorphic to one another, then when we generate the ring of polynomials over those two fields, then they will be isomorphic to one another. Okay, and these two polynomials, p1 of x and p1 prime of x, they are truly going to be corresponding under this isomorphism. So everything's staying beautifully isomorphic, basically. These two fields are isomorphic. They've both got roots to the two polynomials p of x and p prime of x that were the corresponding polynomials initially. Okay, alpha 1 and alpha 1 prime here. Okay, and when we factorize the polynomial p of x and p prime of x in these rings of polynomials which are now isomorphic, then the bits that are left over will be corresponding under this isomorphism. Okay, so everything's going beautifully. Okay, now I do appreciate that, you know, it does take some getting used to all of this. Okay, it's a lot of information to be taking in, but just go over this argument again and again. It does make sense. Okay, right. So where are we going to go now? How are we going to actually find some splitting field for p of x and p prime of x? Well, of course, what can we now say about these polynomials p1 of x and p1 prime of x? This one has degree n-1, and this corresponding one also has degree n-1. So now what we can do is we can use the fact that we have assumed that the theorem is true for the degree of the polynomial is less than n. Okay, I have got you two fields here, E1 and E1 prime, that are isomorphic to one another. Their rings of polynomials are isomorphic to one another. I've got you a polynomial p1 of x and another polynomial p1 prime of x, which, if you like, are isomorphic to one another, corresponding to one another under this isomorphism. Okay, now what I can do is apply my theorem. I can say that if I generate a splitting field for p1 of x over E1, and generate a splitting field for p1 prime of x over E1 prime, and I'll give these names. Let's call the splitting field for p1 of x over E1, we'll call that k, and in fact actually it's probably worth going over onto the other page now. We're running out of space, so I'll copy a bit of this out. So we've got E1 and E1 prime, which are isomorphic to one another. That's what we've got currently. We've got these polynomials p1 of x, okay, and p1 prime of x that are equivalent to one another under the isomorphism between the polynomial rings of these two things. Okay, and now what I'm saying is we can generate splitting fields for these. So we can generate a splitting field for P1 of x over E1, and we'll call that k, and we can generate a splitting field for P1 prime of x over E1 prime, and we'll call that, of course, k prime. Okay, and now I claim that I can instantly say these are isomorphic to one another. Why? Because these polynomials are of degree n-1, so by the assumption that I made that the theorem was going to be true whenever you had a polynomial of degree n-1, I can now say that these splitting fields that I have produced here are going to be isomorphic to one another. Okay, so now what we have to be able to somehow conclude is that these are the splitting fields for p of x and p prime of x. So remember, our task was we had the field f, and which was isomorphic to the field f prime. We had these polynomials p of x and p prime of x, and we were trying to find splitting fields for those, okay, which I'll call k and k prime. They are going to be these things that I've just generated here, which were isomorphic to one another. Okay, so I claim let's use these two fields that I've now generated, k and k prime, which I know are isomorphic to one another. All I need to now show you is that indeed these are the splitting fields for p of x and p prime of x respectively. So I've got these two fields, k and k prime, which are isomorphic to one another from this trick here. All that now remains is for me to prove that they are the splitting fields. So k needs to be the splitting field of p of x over f, and k prime needs to be the splitting field for p prime of x over f prime. Okay, so how am I going to do that? Well, firstly, let's just prove that it is a field extension of f in which this polynomial splits, and the same for this one. Okay, and then let's prove that it's the smallest one. Okay, so firstly, remember that k and k prime were field extensions of E1 and E1 prime respectively. So k prime was a field extension of E1 prime here, and of course we know E1 and E1 prime themselves were field extensions of f and f prime. So E1 was a field extension of f, and E1 prime was a field extension of f prime. Okay, so that means that indeed k and k prime are field extensions of f and f prime. So that's good. K is a field extension of f, and k prime is a field extension of f prime. Good. Okay, now what we want to know is, do these polynomials split within them? Well, the answer is of course yes, because we know that in these intermediate fields, E1 and E1 prime, I was capable of writing p of x as x minus alpha times p1 of x, okay, and I was capable of writing p prime of x in E1 prime as x minus alpha 1 prime, and I'm sorry, that should have been an alpha 1, okay, times p1 prime of x, like so. Okay, and now when we went up from E1 and E1 prime to k and k prime, we were then able to split p1 of x and p1 prime of x into linear factors. Okay, so certainly now in k and k prime I can write p of x and p prime of x as a multiple of linear factors, because this one can be written as a, as a product of linear factors in k, and this one can be written as a product of linear factors in k prime, and we could already do this, put the x minus alpha and the x minus alpha prime in E1 and E1 prime respectively. So indeed, what all of that was arguing was that k and k prime are field extensions of f and f prime in which these polynomials split. Okay, so I can write p of x as a series of linear factors multiplied together in the ring of polynomials over the field k, and I can write p prime of x as a product of linear factors in the ring of polynomials over k prime. So over these fields, these polynomials do indeed split. Okay, so that's good. What we now want to make sure of is that k is the smallest such field extension of f in which over which p of x splits, okay, and equivalently for k prime. So what I'm now going to do then is make the assumption that I can find some smaller subfield, some proper subfield of k in which, or rather over which, the polynomial p of x will split, and then I'm going to find that that will give me a contradiction at some point. Okay, so I want to prove that there is no subfield of this over which this polynomial will split. Okay, so let's say L is a proper subfield of K. Okay, and let's claim that over this field, okay, so in the ring of polynomials corresponding to this subfield of K, that P of x still splits. So I can still write P of x as a product of linear factors. Okay, so that will mean that alpha for 1 will be in there, and all the roots of P1 of x will also be in there. So this means that L will contain alpha, and it will contain all of the roots of P1 of x in the splitting field capital K for P1 of x over E1. Okay, so it will have all of these roots in here. Now I claim that I can find you a contradiction for that. So the first thing I want to show you is that L will contain E1. Okay, so I claim that E1 is going to have to be contained within L. Oh, and by the way, we're making the assumption that L itself is a field extension of F, of course. Okay, we don't want something that's so small that it doesn't contain F. So we're assuming that L is some field extension of F which is properly contained within K. It's going to now contain all the roots that we need for our polynomial P of x in K. Okay, so 1, it's going to contain alpha, and it's also going to contain all of the roots of P1 of x here. Okay, so my first claim is that E1 must be a subfield of L. Now, why is that? Well, we know that E1 was the smallest field that you could the smallest field extension of F that you can possibly generate that contains alpha. Remember the way we constructed E1? We constructed it by taking the ring of polynomials over the field capital F and quotienting out by the principal ideal generated by that irreducible polynomial, F1 of x. Okay, so when you do that, you truly do end up with the smallest possible field extension that you could possibly build that had this root alpha to that polynomial that was irreducible in it. Okay, so if L is a field extension of F that contains alpha, then it must contain E1, because remember, what it means to say that this is the smallest field extension of F that can contain that root alpha is that it is the intersection of all of the field extensions of F which do contain alpha. L is a field extension of F which does contain alpha. It has to contain alpha, otherwise P of x wouldn't still split in it. Okay, so that means that E1 must be contained within this field extension L. Okay, now what does that mean then? That I have a field extension of E1 which is properly contained within K, okay, and also contains all of the roots to P1 of x. Now that's not possible because that will contradict K being the splitting field for P1 of x over E1. That's why I wanted to show you that E1 was contained within L, because now I can assume that L is between E1 and K, and that contradicts K being the splitting field for P1 of x over L. Okay, so I appreciate also that that's a difficult argument when you first see it. But as I say, you'll get used to that. Now, so what I've shown you then is that you cannot possibly have a proper subfield of K which is a which is a field extension of F over which this polynomial P of x splits. And the same argument works here, okay? The exact equivalent argument works here, that you cannot have some field extension of f prime that is properly contained within k prime over which this polynomial p prime of x splits, and therefore indeed k and k prime are the splitting fields of p of x and p prime of x respectively over the fields f and f prime respectively. Okay, so we have now proven what we wanted to prove, that when you generate the splitting field for the polynomial p of x, which is of degree n, then it will be isomorphic to the splitting field of p prime of x, again degree n, over f prime. Okay, so if it's true that this theorem was true for all polynomials of degree less than n, then you can prove by induction that it will be true when the polynomial has degree n. Okay, and since we've proven that it is true when the degree of the polynomial is 1, we can then conclude that it will be true when the polynomial is of degree 2, and then, because it's true when the polynomial is of degree 1 and 2, we can conclude that it will be true when the polynomial is of degree 3, and so on. And we can conclude that this theorem will be true no matter what the degree of the polynomial is, provided that it is, of course, some natural number. Okay, so that then allows us to state that this theorem, wherever it is now, not that, where are we? No, sorry. We don't need that, that this theorem is indeed true, that if you have two fields that are isomorphic to one another, okay, and then you have a polynomial p of x, and the equivalent polynomial in the ring of polynomials over f prime of x is p prime, that if you generate the splitting fields for the two of them, so k, which is the splitting field over f for p of x, and k prime, which is the splitting field for p prime of x over f prime, then they will end up being isomorphic to one another. Okay, and that then allows us to conclude that splitting fields are unique because, as I say, you can make this isomorphism just the identity isomorphism from f to f, and then this statement becomes that if you have two splitting fields for the same polynomial, then they are isomorphic to one another. So we are now truly justified in saying that there is one and only one splitting field for a certain polynomial over a field capital F. Okay, so we can call it the splitting field for a polynomial p of x over a field capital F. Okay, so we will end there this introductory video to splitting fields.